Welcome, everyone. Thanks for being here today on Dask Demo Day. We do have really interesting talks. We're going to listen from Martin, talk about like Dask-GeoPandas, and then what's the progress in there. And then Miles is going to be talking about the guild monitoring in Dask. And then it's going to wrap us up, Guido, talking about two different topics, fine performance Dask metrics and spans. So I would say, let's start with Martin, and then we go on from there. Thank you, Martin.
Okay.
Take the floor.
Hello, thank you. Let me share the screen. I'm also gonna put a link to this notebook to chat, so you can follow it if you wish. I'm gonna talk about Dask-GeoPandas, which is a project which was, I think, originally explored by Matt Rocklin something like 6 years ago. Then it was revived by Julia Signup, who's here sometime after that. And right now it's maintained by Julia, myself, and Joris van der Busche. So it lives mostly under the GeoPandas organization itself. So the pool of maintainers is mostly shared with the GeoPandas project. But I think that I should first start with what actually is GeoPandas, because from Dask-GeoPandas we know what Dask is, we know what Pandas is, but what GeoPandas is. It's a project that extends Pandas by essentially adding a support for geospatial data. So due to some historical reasons, we subclass Pandas data frame and series objects into geodata frame and geoseries objects. And a typical geodata frame looks essentially like this. You have your classic Pandas data frame with index with your data. And we also have another column, at least one, which has geometry D type, which is specific to GeoPandas, and that's a GeoPandas geoseries. And that contains geometric objects like vector geometries you will see soon on a picture. So if you are aware about GIS, ArcGIS, QGIS software for geospatial analysis, GeoPandas is kind of its PyData alternative. I'm gonna go quickly through this. GeoPandas essentially brings different pieces of ecosystem together to one convenient API. So we bring the API, the data, which is the Pandas subclassing and all the Pandas functionality. We have the geometry column, geoseries or geometry array, because it's backed by extension array in Pandas, is containing Shapely geometry. So Shapely is another Python package that is essentially a Python wrapper around the C++ library called Geos, which I never remember what it stands for, but it's some geometry engine something. And that's essentially an engine that takes care of planar geometry and their operations. And Shapely exposes that into Python, and GeoPandas wraps arrays of Shapely geometries into a geoseries object. We also have to deal with projections, which means that if you have a coordinate represented by two floats, we need to understand whether that actually means latitude and longitude, or whether that means something else, and where on Earth it actually is located. So for this reason, we use another C++ library, which is called Proj, and we use Python wrapper called PyProj, or Proj. I don't know what is the ideal pronunciation here. And the final part is dealing with geospatial file formats, like shapefile, GeoJSON, GeoParquet, and similar. And for that, we need yet another C++ library, which is called GDAL, which is available in Python via Fiona wrapper, or recently our own PyAgree wrapper. So diagram kind of looks like this. We take all those three C++ libraries, their APIs in Python, and together with Pandas link all of that into GeoPandas, and which then supports the rest of the ecosystem, including some spatial analytics and statistics and other use cases. To illustrate it on actual data, GeoPandas still comes with built-in data sets. It will no longer be the case soon, so you can see the deprecation warning in here, but we can still read it, and you see that in this case we have a geodata frame where the geometries of countries around the world. So this part from this column to the left is very pandas-like. This one is the geometry one, which contains our geometries. So we have polygons, we have multi-polygons, which kind of capture areas. We can also have line strings, which would capture something like street network or railway network, or just a boundary around something, or we can have points or multi-points. It's kind of the typical set of geometry types we deal with. For the sake of simplicity, I'm going to remove Antarctica, and I'm going to show you a couple of operations GeoPandas is typically used for. One of them is, for example, creation of a convex hull, which is an area which not necessarily area, but it's a polygon around different polygon, which kind of ensures convexity. I will show you how it looks like on a map very soon. We do have a concept of an active geometry in GeoPandas. So even though you can have multiple geoseries columns in the data frame, one of them is kind of seen as the active one. So if I call the geospatial method or property directly on the data frame, it will use the active one, but I can also specify a different column. So in this case, these two are actually equivalent because geometry is the column, the only column which is there. Right now, we also have the convex hull column. So we have two geometry columns, but this one is called the active one. If you try to plot it on a map, which is another functionality of GeoPandas, we will see that we have geometries like this. The blue ones, those are the original geometries. The red outlines are the convex hulls. So you can see how the convex hull kind of wraps around different shapes and what convex hull is. This is one of the typical geospatial simplification operations. I mentioned that we are dealing with projections, kind of knowing where on Earth these points actually are. There's a property for that with some information. This is actually a PyProj object, and in this case, we know that we are dealing with the coordinates which are actually in degrees, latitude and longitude, covering the whole world. But we can also reproject it to different ones. So this is the EPSG code for the web Mercator projection, the one you are very used to seeing on Google Maps or other map services. So if I reproject it using 2CRS, we can see that the map looks slightly different. For example, Greenland is significantly larger right now. So don't forget that every map of the world essentially lies to you about something, either angles or areas or combination or even something else. And that brings me to Dask-GeoPandas. In the same way as GeoPandas extends pandas, Dask-GeoPandas tends to extend Dask. That's to say Dask data frame, essentially. So we opted for the similar model, and we subclass Dask data frame into Dask-GeoPandas geodata frame, where each partition is a single GeoPandas geodata frame. So far, there's not a lot of differences, and there will not be a lot of differences because we're trying to keep it as similar to typical Dask data frame experiences as you can have. But a couple of differences, a couple of functionalities that are in Dask-GeoPandas already, that you can create your partitioned Dask-GeoPandas geodata frame. It's a bit mouthful. From GeoPandas object from memory, but you can also read it directly from file. Thanks to PyGrio, which means that you can essentially read traditional geospatial file formats in parallel. It's not that straightforward because not every file format expects this kind of treatment, so sometimes it's suboptimal. But there is another solution for partitioned I/O and reading efficiently large geospatial file format with large geospatial data, and that's GeoParquet. So I suppose you are familiar with Apache Parquet file format. There's an extension called GeoParquet, which contains a specification on how to store geospatial data in Parquet. And I think that GeoPandas and Dask-GeoPandas was the first implementation of this, and this is currently on its way to becoming a standard file format for geospatial analysis, like standardized by the entity that standardized this within the geospatial world.
We got 1.5 more minutes.
All right, super quickly go to one thing that is very specific for GeoPandas and Dask-GeoPandas, and that's partitioning. I need to read this file first. So if you get a file of airports around the world, which looks something like this, we do have an issue, because if we try to get the boundaries of these, of the partitions, we see that it's kind of everywhere. The issue with this is that the spatial operations will be inefficient, and another issue which is underlying to this is that we need to partition data according to 2 dimensions, X and Y, but our object is 1-dimensional, it's a data frame. So we use something called Hilbert curve, which is a space filling curve. That's one line going across the whole extent of your area, according to which you can sort the geometries, and then you can spatially shuffle your data frame to get partitions that look more like this. And this is kind of the core of efficient geospatial operations. We do have some other operations coming from GeoPandas, but we also have some limits in here, what is not necessarily supported. We do have an issue with overlapping computation currently, so we do need it, but since our data are spatial and 2-dimensional, we would need overlapping computation that goes in 2 dimensions, which is not super straightforward to implement on top of that data frame. Spatial indexing is more kind of like geospatial specific stuff that allows us to quickly and efficiently select geometries based on their spatial location. That currently works within individual partitions, but it's more complicated to do that over the distributed data frame. And we do have some trouble with memory management because the geometries are actually pointers to C++ objects, and there has been some weirdness around that we haven't fully resolved yet. So you may see some workers running out of memory occasionally. I think my time is up. Thank you.
Yep. Good. Thank you, Martin, very much. We have time for like maybe one question, and then if at the end we have remaining time, we can circle back. Do we have any questions for Martin? Looks like we don't. We can circle back at the end. If you have any questions in the meantime, then you can post it on the chat. And in the chat, there's also the notebook. So we'll post the notebook back on the issue then again for when the recording is back. So now, next up, we're going to go with Miles, who's going to talk about the GIL metrics in Dask. So Miles, do you want to take it over?
Okay, so I am going to talk about the GIL monitoring introduced in version 2023 4.1 release of Dask Distributed. It creates kind of a high-level overview of the amount of contention that the GIL is under running your code in Dask. And those I'm sure many, if not all people are aware of what the GIL is. It's essentially this, if you Google or DuckDuckGo this global interpreter lock on Python, you'll come and find that it's basically a mutex that protects access to Python objects. Lots of interesting information. What I'm going to talk about here, and the reason kind of that we added it, is generally speaking, broadly speaking, the GIL can degrade performance even when it's not a bottleneck, and more detailed slides there. So moving on, you can tell I'm not as well prepared as Martin. My slideshow is tabs. You'll probably want to use PySpy. It's, I think, more accurate representation of the GIL contention among many, many other things that you can monitor from it. But if you scroll down here, you can find that it does support monitoring of the GIL. And there's kind of like some interesting things about this, is that, namely, I think it's like the Py interpreter state is an opaque object that varies between Python versions and architectures. So you can't really poke at it reliably to find exactly what the GIL contention may or not be. So what they do is they find those offsets, and then they're able to poke at it reliably and find those things out. But the main issue, maybe for other people, is that it's typically used as a command line interface. So it's not like you can, that I'm aware of, put it into your code and kind of say, measure this bit of code right here and tell me how much contention for the GIL that this block of code is causing me. So then enter this other project here, GIL knocker, which as the name implies, kind of just knocks and asks for the GIL many times at different configurable intervals. What it does is it will ask for the GIL, time how long it took to acquire the GIL, and then immediately release it. And then do that for a certain sampling period. And then from there, just relax and not do anything for a certain sleeping interval. And so that does come with a caveat of looking at the trade-off of time. So this is a terrible graph, mind you, but what we have is sort of 3 sections measuring various amounts of like GIL contention, simulated GIL contention. So first we have a lot of GIL, and none representing like no sampling. So basically what happens if you have a lot of GIL, it doesn't really matter how frequently you pull the GIL to find out how busy it is, because the GIL is going to be taken kind of regardless. So it'll just kind of sit there and just wait for the GIL, more or less. Most of the impact will be found if you have a little GIL, because then GIL knocker in this case, or the method of which it uses, is creating contention on its own. So these are more or less ordered. You can see like when it's like 10 milliseconds, 1 millisecond, it's effectively the same as not monitoring at all. But then from there, as you like get ever faster or more frequent, then you can have like a slight increase. But again, you can kind of offset that a bit on the like the sleeping period, for example. Like you can ping it really hard for a short amount of time to get a quote more accurate measurement, and then sleep for a longer period of time. So try to mitigate that. And then some GIL, it's kind of all over the place. So then you're kind of safe for the most part. Again, if you kind of go down to the really low, like 1 microsecond, then you're really causing some contention there. But anyways, that's kind of what Dask Distributed is using under the hood to get these metrics. So now I will just run some demonstrations to visualize this. And so now actually, let me just go with this first. So there is a blog post here about how to enable this and what it is. And essentially, all you have to do is install GillKnocker, and it will be enabled by default. So if you don't have it installed, it won't be there, and you won't be able to see anything. But if you do have it installed, then you will have this contention plot, which by default will just have the event loop contention as you had before. But again, if you have it installed and enabled, then you will have these two additional ones, one for the scheduler, one for the workers, and this is averaged across the workers. So on the left screen, I have a small tiny cluster going, and then we can kind of simulate the lot of Gill thing. So this is just a for loop incrementing over across the workers. So if we run that, it's basically, it'll go all the way up for the most part, more or less. So you see that it's like high 80s, 90s. Again, this is kind of tuned like on the, we'll say the conservative aspect of things. So you could increase the polling interval and get a more accurate representation, because if you run this same code with like PySpy, you'll get like mid 90s, for example. But this will give you like an inclination of like the default settings, which are again mentioned in the blog post that you can adjust as far as the interval, how frequently it's polling. So defaults to that. Yeah, so that was a lot of Gill. You can see that goes up, and then getting mildly better, we can create a time series and do some group buys, and then you'll see that this is less, but still some Gill contention going on there. So like 60, and then there's also should have went to this one also. If you go to workers, then you can see the individual, if that's at all interesting to you, then it's also going to be available there. So once that's done, then it can get, even better, kind of demonstrating like worse, better, and then less Gill contention. If we just use like Dask array, for example, it's better still. And of course, if you're just doing straight NumPy, I guess for the most part, then it'll be better still. But just to demonstrate that, okay, now it's a bit lower when you're using like Dask array stuff. And I think I've more or less covered everything I was after. I will post the link to the blog in the chat if everyone's interested. Is there any questions? Otherwise, I think I'm mostly done here.
Awesome. Thank you, Miles. Yes, folks, if you have any questions for Miles, this is your time to ask. Everyone seems to be very quiet today. I guess I'll have a question, Miles. Like, in which situations do you envision like the user or the average user taking a look at this? Or this is mainly for advanced users trying to understand a little bit better about their code?
Good question. I would say that since it's giving a high-level overview of the Gill contention, you could use it as a bit of a litmus test for if you're trying to debug some performance issues and you have a suspicion that maybe lowering the Gill contention might help out. But then you can fire this up and say, okay, well, it's like 40–50%. Maybe I shouldn't invest any more time investigating that, and maybe troubleshoot some other things first. And then
what
go into
percentage?
PySpy.
At what percentage should I start getting worried? Or eyeball?
Yeah, I don't know. I suppose that various other people might have input on that, but I would assume, yeah, Guido.
I will show in my demo when you start getting worried and how your tool is super useful.
Okay, super.
Awesome. So that's a great segue. Miles, if you wanna, I put one of the blog's links in there, but like if you want to post it on the issue of today's Dask Demo Day, then that will be great. With that in mind, then let's just let Guido carry on. Guido's going to be talking about two different things, and the demo is going to be a little bit longer, so brace yourself. And I would say if you have questions in the middle, feel free to post in the chat and interrupt, or if you're not comfortable interrupting, post it in the chat and I'll interrupt. Awesome. Guido, take it over.
Okay, so I will be talking about performance analytics. So the next release of Dask is going to feature two brand new tools, which are spans and fine performance metrics. So historically, we've already had the breakdown of our workflows in terms of how long each task group or task prefix took overall. And we could already investigate, okay, why am I spending so much time in this task? What we didn't know, however, was what are tasks spending time on? Are they running the CPU? Are they busy doing IO? Are they locked on the GIL, etc., etc.? So fine performance metrics want to give answers to this in some nice usable format. So I have here Jupyter Lab. I started a cluster and I am gonna drag a new widget into it. There it is, fine performance metrics. You don't need to install anything particular, it's just there. If you're not using Jupyter Lab, you can also go to the traditional GUI and click more and find performance metrics, and it's the same thing. Now I'm going to run a demo workflow. Just create some data set and do an aggregation. And you see how the widget in real time starts aggregating in performance information of what the cluster is doing. And in a few seconds, while this is updating in real time, and in a few seconds when this is finished, okay, I'm gonna analyze what I'm seeing. So in the center, I am having a grand total of 461 CPU seconds worth of worker activity. You will say, wait a second, the whole thing lasted 8 seconds. Yes, but I'm running on 32 threads. So 461 divided by 32, you will get the wall time we just experienced. And where did we spend time during this? Well, 60% of the time, we spent it inside tasks running the CPU. This is more or less universally good time, and we like it. If our algorithm is performant serially on pure pandas or whatnot, then this is all good, 60%. And then we have a wealth of other stuff, which is probably waste. 40% of our end-to-end time was wasted. And where did we waste it? Well, 30% was inside the threads, but without consuming the CPU. Now, this could be IO, this could be GPU time, or this could be GIL contention. If I look at my workflow web, I have neither IO nor GPU. So I'm getting a strong feeling here that these may all be GIL contention. So this 30% of time spent in the thread not using the CPU, where did I spend it? Well, I don't have any IO, I don't have any GPUs, so my question is it the GIL? Well, let's go and find out. Contention, which is what Miles just demoed a second ago. And I'm gonna rerun, and I'm gonna look at the contention meter in real time. 70%, GIL contention, 90% GIL contention on the workers. This is as much of a smoking gun as it can possibly be. We are wasting a quarter of our time because of the GIL. And so if we want to make this thing faster, we're going to investigate why we are spending time on the GIL. And I can look at it and say, okay, what functions am I spending time in? I'm now looking at the chart in the bottom left, which is broken down by function. And it says, okay, get item is by far the biggest source of time consumption, both CPU and non-CPU. And then I have two more, and then trivial amounts of everything else. And I can filter, for example, I can do cherry pick what I want to see, and my pie charts update in real time. And I had a quick look, and that time series uses pure Python strings. And that is why we're seeing this much GIL contention. If I swapped to PyArrow, that would disappear. Another thing that is interesting is the pie chart on the right is my network transfers. Here it's saying that I spent 45 seconds in sending data to other workers. And then I spent an extra 2 seconds just serializing the data. Again, that is not terrible, but it's substantial. And that tells me already that I have pure Python data because PyArrow data serializes instantly. And also that time will also block the GIL. So it all boils down to the same source. Not necessarily at all times, but in this use case, I have pretty much a very clear idea where my problem is. It's GIL contention. And then if I look at my data, I realize I have Python strings. I am going to show another use case, which is also very interesting in my opinion. Now I have a Dask array workload with a dot product, and I sized this problem so that it would start spilling. So this problem cannot fit in RAM, and so I am swapping in and out of disk. So when you start seeing gray on the memory charts on the left, on the top right, a lot of people, including myself, get really anxious and say, I don't have enough memory, this is low because of spilling. Is it though? So I have just finished solving this problem, and the fine performance metric tell me, pie chart in the middle, 96% of my time was good, healthy CPU time. And I wasted a grand total of 2% on spilling data. This is extremely good. This tells me that if I were to spend a lot of money increasing the amount of RAM available on my workers, I would get at most a 2% performance boost. This is this specific use case. In other situations, you will find spilling and unspilling activity absolutely hammers you end-to-end runtime, and this tells you, oh yeah, you don't have enough RAM, you need to increase. On the right, I see the same thing, but for network transfers, I have 12 seconds worth of good network I/O, and I have 1 second worth of reading the data from disk because it was not already present in memory. Again, it seems substantial in this case. I know that I have enough memory, and even if I'm seeing gray in the memory plot, it's not a big problem. And metrics are not just about wall time, they also show different kind of information. For example, I can show bytes. And here I see that whenever I am reading, I'm starting a task, I have a 79% cache hit. What does it mean? 79% of the time of the data that was read to start a task was already available in memory. And only in 21% of the times I had to stop and slow down because I had to retrieve from disk. And this is, again, a decent cache hit rate, and in some cases it will be much worse. And same for data for network transfer, 81% cache hit rates on the on network transfers in terms of bytes. In terms of number of tasks, I can switch to count, and I see that I had 147 tasks that were just loaded immediately from memory, and 170 something that were loaded. Sorry, 25 tasks that were loaded from disk. I'm gonna go to another use case to talk about spans. Now, you see that I have been reloading my cluster to clean the data every time. And this is pretty frustrating, and I really don't like it. So I wonder, what if I could tag pieces of my computation to know downstream what they are about? And these are called spans. Spans are a client-side decorator and the context manager, where I can say, I can put an arbitrary tag on what I'm doing. For example, here, I am calling my whole end-to-end thing my workload. Inside it, I have a subspan called data load. And here there is one or more stages of my graph. Then I am calling this thing, which, for example, could be a library function, which would be very, very big potentially and do many, many operations inside. And this thing has been decorated with .product self, and we will see it tagged accordingly. And so I have run this workload, and down below, this is the same workload as before, by the way. And here you're seeing exactly the same as before. So I didn't do anything about spans, but the grand totals are the same. Now I can filter by span. I can filter by my workload. Of course, nothing will change because I don't have anything else. But I can also say, okay, let's see just the data load stage. Just the data load stage was this. And it took 2 seconds in total, that random generator. And as a developer, this made me quite excited, because this random function, we know it to be fast, but we never ask ourselves, how fast is it? The answer is not great, actually, because I'm spending a quarter of my time just unpickling the metadata from the graph. So I could make it faster as a Dask developer, just tweaking this thing. Again, is it worth it? Well, yes and no. So this is random sample, but if I go back to the grand total, random sample is this third thing from the left is a tiny fraction of my end-to-end workflow. So for this use case, if I was tasked to optimize this use case, I would not spend time on optimize my random number generator. If I had something that is much more heavily reliant on the RNG, then I would go there. This lets me know where is the money. How can I best spend my time debugging performance? I can go straight into the worst offenders and not waste my time on a gut feeling of, oh, this may be faster, but no, I know exactly where I'm spending the time. And if I see something massive, I can spend my developer time reducing that and ignore all the bits and bobs that are actually not substantial. Now I'm going to run something different. I'm going to create a new top-level spans, and I'm going to run the other workload. And notice that this time I am not going to bother restarting my cluster. And as this thing goes, the new tasks are going to appear in the graph of the grand totals. And if I just want to see the new stuff, I'm going to select by span time series. And this hides completely all my previous Dask array workflow. And maybe I will go back to my workload, which was my Dask array. And this completely hides the time series workflow, and so forth, so on and so forth. Maybe I'm interested, I have a very complicated workflow of many different things going on, and I would want to know, okay, but how much time am I spending in calls to this specific library that I'm calling from many different places? I could just select .product self, which is, for example, my library, and it would tell me exactly the grand total for that library. One last thing that I'm going to show is that you don't just have built-in metrics. You can expand with your own. For example, here we have some dummy tasks which we send with client.submit. We have an IO intensive task, which spends 0.8 seconds doing something we don't know, probably optimizable. And it spends, at some point, it starts doing IO, and we know that that time is probably good. I mean, we would like to also see how long it takes. Maybe we could speed up our hard drives or our network if it's too slow. And maybe it's also reading, for example, from a infrequent access S3, which costs money to access every time. So I will also keep a tally of how much I am doing that. So, okay, metered IO, and let's say I just read 1 gigabyte. This is a custom metric that is called, which is completely arbitrary labeled metered IO. And it says log 1 gigabyte under this. This is an automatic timer that says everything that runs inside this, measure the time and label it as IO and subtract it from the grand total of the task time. Below, we have something somewhat similar. We have a standing for a task that calls the GPU. And again, we have say, okay, we're going to enter the GPU now. We know the CPU is going to be idle. That is okay. We are not on the GIL. We are on the GPU, and we want to note that. And we're going to spend 0.7 seconds there. And then we're going to say, okay, but what if we want to record a time that is not wall time, that doesn't add up to the grand total runtime of the task? Fine, just change unit, and I'm going to use a completely arbitrary unit, GPU seconds, and an arbitrary label. And below, we have the result. So the two tasks are here. The GPU task spent 700 milliseconds on this completely arbitrary label, GPU. IO task spent half a second on this label IO, and 800 on everything else. The grand total of the task was 1.3, and the fine performance metrics did the math for me to tell me, okay, this I don't know about. These 800, I don't know where did they go? You should investigate. And I can go Unix selection, and I can go to bytes, and I can see IO task. I have this label, metered IO, 1 gigabyte. And I know which task generated that metered IO. I could go to GPU seconds, and I see that the GPU task spent 123 GPU seconds, whatever that unit of measure may mean, on running GPU task. I am done. Are there questions?
Thanks a lot, Guido. I'm surprised that no one has any questions. Come on, someone has had a question.
Letting it all soak in still. That was cool, Guido.
I'm curious about this time sleep. What happens if your task is actually shorter than your sleep?
How can your task be shorter than the time you're sleeping inside it?
You're not sleeping when you're measuring, right? You're only sleeping inside the task.
I am, so that sleep is a stand-in for whatever I'm actually doing.
Oh, okay.
Those are
This is your
tasks.
work. Okay, this is
So
not your measuring.
IO task is taking 1.3 seconds end to end. And in this case, is not consuming any CPU. Now, I have something that automatically measures how much CPU time I'm using. That will be shown as thread CPU, as I was showing before. However, I, as a developer of this task that I'm now sending on the task cluster, know that a certain segment of it is IO intensive. So I want to tell the observer, this is not thread non-CPU, this is time in the thread. Yes, it's not consuming the CPU, but I know why. And this why is because I am on IO. And of course, this may tell me, doesn't just tell me you are not spending time on the guild. This is also telling me, is my IO layer a bottleneck? Is my network fast enough? Are my disks fast enough? Or should I speed that up?
Okay, yep, that's cool. Thank you.
There was a suggestion about, I don't know, Miles, if you saw it on the chat, about probably making the guild contention output like a overtime plot. Martin posted something there. If you eventually want to interact with him later on, that will be great.
Yeah, and I like that Hendrik brought up that it is already, that portion's already exposed in the Prometheus metrics. Yeah.
Cool. Guido, if you have like this, and if you can make this notebook public and then post it on the repo, sorry, on the GitHub issue, as well as like all the other folks like sharing the content that you presented today there, that will be great. When the recording is up on YouTube, I will post it back there and then like tweet about it. But it's been great hearing from you all. If we don't have any more questions, that will be it for the demo today. Yep. Any other questions? If you want to present, then you can register in the community issue that we have, that I'm going to find it now. Any of you has something that you want to talk about? We're still looking for people for the next session on July. So far, we have only one presenter. Today was a specific case that we have like a longer time with Guido. He was presenting like a longer topic, but in general, we're aiming for like 5 to 7 minutes for each demo. And yeah, if you want to present about something, just shoot a message in that issue that is on the chat, and we'll add you to the list. All right. Thank you, everyone. I'll see you in a month, and some of you probably earlier. Have a good day.
Thanks, everyone. Thanks, Natty, for organizing.